Hello everyone and welcome back once again to this course on aluminum based alloys and metal matrix composites. So in the previous lecture we were talking about aluminum silicon alloys, and we have seen the morphology of the silicon as it grows during the solidification of these alloys, and we have also discussed about what could be the role of such morphology and so on. Okay. So let us continue on that and see how this morphology can be modified and what are the mechanisms of such growth. Okay.
And this is what we discussed in the previous class as to why silicon grows in a particular morphology, which is kind of flaky or needle-like morphology, like what you see over here. For example, this one, right? So this is the aluminum silicon eutectic, which forms in this kind of aluminum silicon cast alloys. And we were trying to understand as to why this kind of morphology forms for silicon when this alloy solidifies. Okay, and with regard to that, we first of all discussed what kind of structure silicon has, and what it takes for silicon to form a stable nucleus, and that is nothing but two of these tetrahedron. If these two tetrahedron combine, it can form a stable nucleus for silicon, and then it starts to grow in a particular direction. That's what we discussed, and that particular direction is the 211 directions, as you could see over here. And this happens through a mechanism which goes by the name Tpre, that stands for twin plane reentrant edge. Okay, so this mechanism tells you that when a twin forms in the silicon crystal, and if there are two twins, then along these twins you have these reentrant edges, which are the preferential sites for the silicon atoms to attach, right? So these edges are kind of preferential nucleation sites for the silicon to grow. Okay, and that is why when it grows in this particular direction, that is 211, a particular kind of morphology like flake or needle that we have seen will form, because in this particular direction only it will lead to more and more these reentrant edges, and as a result of that, more and more growth will take place in that particular direction. Okay, so this is what we understood in the previous class. Now the question would be as to how to stop this growth in this kind of morphologies, because such morphology is many a times not good for some of the properties such as the ductility and the fracture toughness, etc. Okay, so therefore at times there is a need for modifying this morphology and make it more uniform, like what we have seen in this particular micrograph over here. Instead of this kind of needle or flakes morphology, if we could make it this kind of fibrous, then it will be better for many of the properties. Okay, so the question would be how to do that, as to how you modify this kind of morphologies into a fibrous kind of more uniform morphology. Okay, so that is what we are going to talk about in today's class. So in order to modify this morphology, you will have to stop this growth in this particular direction. Okay, so therefore we will have to do something so that the growth happens in all possible directions randomly instead of in a particular direction, right? So therefore we need to identify the mechanism first, and that is why we had to first discuss this. Once we understand the mechanism of this particular growth in a particular direction, we can also understand as to how this can be retarded. Okay, So we have seen that in this particular case or this particular mechanism, we have this reentrant edges which form due to these twins that you have in the silicon crystals, and these are the sites for the preferential growth of silicon. Okay, so if we could stop silicon atoms from attaching to these preferential sites, then this growth can be prevented in a particular direction, and you can expect the growth to occur in all possible directions randomly. Okay, so what we need to do in order to stop this growth, we need to poison these preferential sites for the silicon to attach. Okay, so that is what is done when you do this modification by some minor additions that we talked about before. If you remember, in this particular micrograph, you have a small addition of strontium. Okay, so this is a modifier which was added to modify this morphology, right? So when you do this kind of additions, it can actually retard this particular mechanism of growth, right? And how it does is, when you add certain elements which are known as modifiers, as I said, in small amount, they will basically promote some kind of poisoning by poisoning those sites at which the silicon atoms tend to attach more preferentially. Okay, so this mechanism of modification when you add certain elements in small amount is known as impurity induced twinning, or in short IIT. Okay, so the name sounds very familiar, IIT, but the meaning is different over here. Okay, so this theory, this IIT theory of modification, says that the chemical modifiers are actually adsorbed onto the surface in places such as, in locations where you have this kind of steps and kinks on the surface. Okay, so on the crystal surface, if you see, it is not completely perfect. There may be some defects such as some steps or this kind of kinks. So in these places, these modifier atoms actually can get attached to and poison the growing atomic silicon layers. Okay, so the layers which are growing in a particular direction will not be able to grow when this kind of modifier atoms are there on the surfaces present in different locations at certain defects like this, and thus it will prevent the attachment of the silicon atoms to the crystal in the preferential sites. Okay, so that is how the preferential growth of the silicon can be prevented when you add this kind of impurities. Okay, and that is why this particular mechanism is known as impurity induced twinning. Okay, so this will also promote more twinning like what you have seen in this case, but here the sequence of the stacking of the atomic layers will be altered. Okay, so it will promote more twinning by altering the stacking sequence of atomic layers. Okay, and you can therefore expect the growth of fibrous branches along these locations where these impurity atoms attach, and therefore the newly added layers will seek to grow around the adsorbed impurity atoms. So what it essentially means is that the layers which will grow now, when you have the presence of this kind of impurities, they will branch out, which means that they will tend to grow in other directions also, rather than growing in a particular direction as you would have seen before in this particular case. Okay, so that is how, by attaching to this kind of places on the surface and promoting more twinning, these impurity atoms will prevent the growth of the silicon crystals in a particular direction. Okay, so this is how this particular mechanism, impurity induced twinning or IIT, works in terms of preventing the preferential growth of silicon. Okay. There are other mechanisms also. If you look at this here, for example, which is restricted growth or the Tpre poisoning theory. So here the theory suggests that the modifier atoms which are added are adsorbed selectively at the reentrant edges. Okay. So instead of silicon atoms, now you have these impurity atoms which are added in small amounts, right? So now that these reentrant edges are already occupied, it will prevent the further attachment of the silicon atoms along these reentrant edges, and therefore it will retard the anisotropic or the preferential growth of silicon in a particular direction. So that's what the meaning of poisoning here. It means that it will poison the sites at which the silicon prefers to attach. Okay. So as I said before, the reentrant edges are considered the favorable or preferential growth site for the silicon crystals, and therefore when the modifiers are already present in these edges in this kind of locations, then it will deactivate the Tpre mechanism. Okay, as I was mentioning, it will prevent the silicon atoms to get attached to this kind of reentrant edges, and therefore you can expect the anisotropic growth to stop. Okay, so the restriction of rapid growth along that particular direction, along the 1, 1, 2 directions, will occur. Okay, the growth in these directions will be restricted because of this poisoning effect. So in other words, you can say that an isotropic growth in several directions instead of a particular direction will occur, and this will prevent the formation of the flakes, and therefore you can expect a more uniform or fibrous kind of morphology in the solidified alloy. Okay, so this is how, you know, the addition of impurities or some other elements in small amount can prevent the growth of silicon in a particular direction and modify the morphology. And apart from the additions or modifiers, there are certain other techniques also which can be used to modify this kind of morphologies, and one of them is by rapid cooling. So during the solidification, if you increase the cooling rate, that can also lead to modification of the flaky structure of the eutectic silicon, and the mechanism is explained with the help of this diagram over here. So here you have aluminium and silicon growing together. Okay, and heat is continuously being extracted because the alloy is solidifying right now. So the thermal properties will come into play in this growth. Okay, so if you look at the thermal properties of aluminium and silicon, they are quite different from each other. The thermal conductivity, for example, are very different or significantly different. The thermal conductivity of aluminium is much higher, around 205 watt per meter Kelvin, while for silicon it is only 83, right? So it's significantly higher. The thermal conductivity of aluminium is significantly higher than silicon. And if you look at the latent heats, the latent heat of fusion, There also you have a significant difference. Here the trend is opposite. Aluminium has a much lower latent heat of fusion compared to silicon. Okay, so for aluminium it is only 396 joules per gram, while for silicon it is 1411 joules per gram. Okay, so because of such huge differences in their thermal properties and also the latent heat of fusion, aluminium will solidify much faster than silicon, right? Because as you could see, the thermal conductivity of aluminium is much higher, so therefore it will lose the heat much faster compared to silicon, and therefore it would tend to grow faster compared to silicon while it is being solidified. Okay, and that can be said from the latent heat of fusion also as to why aluminium will solidify faster compared to silicon. Okay, because here latent heat of fusion is also much lower. So both of these combined, that means a higher thermal conductivity and a lower heat of fusion will ensure that aluminium will solidify much faster compared to silicon. Okay, and therefore the aluminium grains will lead during the solidification. So this is what you see in this particular figure over here in figure B. Okay, so this is, let's say, in the beginning of solidification, where the aluminium and silicon crystals have just begun to grow. And as the solidification proceeds, you can see aluminium beats silicon as it grows faster, right? And eventually, what happens is, as the cooling rate increases, aluminium will lead more and more, and it will actually cause a complete encasement of the silicon growing crystal, as you could see from this particular figure over here, figure C. As the silicon lags behind and aluminium leads, this will result in a complete encasement of the silicon by the growing aluminium crystal around it. Okay, and therefore you can expect that the growth of silicon in this particular direction will be retarded, right? So this is how the preferential growth of silicon in this case can be stopped due to the encasement of these leading aluminium crystals which are present before the silicon crystals. Okay, so this is another mechanism or another way of modifying the flaky structure of the eutectic silicon to make it more uniform or fibrous kind of morphology. So this was about the cast alloys. Okay, so now let us go back to the other aluminium alloys. So in the other category we have the wrought alloys. And here we have seen that we have these alloys. Which starts with a digit followed by another 3 digits. Okay. So we have already discussed the significance of the first digit. This basically specifies the major alloying element or elements present in a particular alloy. 1000 we know is for pure aluminium with different levels of purity which is specified by the last two digits. Okay, and for the alloys that is starting from 2000 to 8000, the other digits that we have, that is these three digits, they have some other meaning. Okay, so first digit, as I said, for the alloys will specify the alloying element, the major alloying element. Now let us see the second digit as to what does this stand for. So this is basically related to variation in a specific alloy, variation in terms of the composition. Because what happens in many cases, a tight control on the composition or the impurity level is required for particular applications needing certain properties, and to achieve those properties a tight control on the impurity has to be done. Okay, so this second digit signifies what kind of control has been exercised to obtain those compositions for a particular property or properties. If the second digit is 0, then it indicates that the alloying elements have been added to aluminium with whatever impurity it had, okay, without much of purification. So it basically points to the commercial purity level of aluminium in which the other alloying elements have been added. So this essentially says that aluminium with commercial purity level makes up the bulk of the alloy. And rest of course will be the other alloying elements as per the composition of the alloy. When the second digit is an integer between 1 to 9, then let us see what is the significance of that. It basically indicates that some control has been exercised to control the impurity level to come up with a particular composition which is needed to control certain properties, okay, or to achieve certain properties for a particular application. For example, the basic 7000 series alloy can be assigned to this 7075. So this 0 basically indicates kind of, the first generation alloys, as I said before, with commercially pure aluminium into it. And then if you see other variations in this, having the second digit between 1 to 9, such as 7175, 7275, and so on, this indicates that there was some bit of control which was exercised to refine this alloy from this 7075, which had the commercial purity level for the aluminium. Okay, so this 7075 was the original alloy, as I said. And when the fracture toughness comes into picture, with the impurity levels in this alloy, the required fracture toughness for many applications could not be achieved, and therefore the impurity levels had to be controlled to obtain the required fracture toughness, and therefore these other variations having the second digits from 1 to 9 came into being. And out of this, from 7175 to 7475 are the alloy which are still active and are known for their superior fracture toughness. So like that, it is true for other series of alloys also, when you have the second digit changed from 0 to any other integer. Now let us look at the third and the fourth digits. While in pure aluminium, that is in the 1000 series, these two digits indicate the purity level, but in the alloys, these two digits, that is the third and the fourth digits, do not really have any particular significance. They're used only to identify a particular type of alloy in a given series. Right? And they do not have any other role assigned to them. And their sequence also does not mean anything special. Now, if you look at the alloying elements in these rod alloys, in the 2000 series, copper is the major alloying element. So if you look at the effect of these alloying elements, here copper imparts strengthening due to the solid solution hardening mechanism that comes into play when copper is added. And apart from that, copper can also impart precipitation hardening. So therefore, 2000 series alloys are heat treatable alloys. Then in the 3000 series, we have manganese as the major alloying element. Manganese provides a moderate increase in the strength, but they have relatively high formability and ductility. Aluminium manganese alloys are also known for their good corrosion resistance. In almost all kinds of environments. 4000 series belongs to the aluminium silicon, but as I have mentioned before, this is basically assigned to the aluminium silicon cast alloys, and these alloys are not really part of the rod series. Okay, and we have already discussed these cast alloys. Next we have the 5000 series, where magnesium is the main alloying element. And among all the alloying elements in the non-heat-treatable category, magnesium provides the highest strengthening effect. I should also mention here that these non-heat-treatable alloys, which cannot be strengthened by precipitates, can be subjected to strain hardening when it comes to improving the strength. Then we have the 6000 series. Here we have magnesium and silicon as the major alloying elements. And as we have seen before, this is also a heat treatable alloy, and magnesium and silicon combine to provide that hardening precipitate Mg2Si. These are the alloys which can be easily extruded and therefore can be formed into different kinds of products and shapes. In addition, they can also be readily joined or welded by almost all commercial processes which are available for joining. Then we have the 7000 series with zinc, and this is also a heat treatable alloy. And these are the one of the most strongest in the aluminium alloys. And finally, we have the 8000 series with lithium. These are also heat treatable alloys. And sometimes we have copper and magnesium also, which can give rise to additional precipitates and hence additional benefit on the strength.
And with that, we come to the end of this lecture. But there are more to come. So I'm going to see you soon again. Thank you for your attention.